that we please. We have to make sure that the initial value we choose does not make f prime 0 of that value. And now there is another restriction, which is less of a problem. Do not choose x0 that has a max or min between between x0 and r. The method will never converge. So this is less of a problem. And we will realize if the method doesn't converge, then we will realize that something is wrong. So what am I saying? Let's say this is the R I'm looking for, and I'm starting with x0 here. So there is a max or a min between the starting point and the solution. The method will never converge. I will never get closer. It will stay here forever, forever. It will never get closer to R. It will get closer to this, but not to R. Okay, I will determine this solution, but if I have something like this, and I start here, it will never converge because there is a max or a min in between. That's all this says. Okay, back to our graph. Okay, so Newton said, fine, we got a better estimate. But he said, well, I can do better. And he continued. He drew a vertical line. It crossed the graph in this point. Of course, now this point is x sub 1 comma f of x sub 1, this point. What do you think he drew next?
Tangent.
Of course. He drew the tangent. He extended it. He called this point x sub 2, I'm jumping, comma 0. Now, here's the question. Is x sub 2 a better estimate of r than x sub 1 was?
Yes.
Of course, because it's so much closer. And then he said, okay, we're not going to stop. We're going to continue. He drew, of course, you cannot see whatever I'm doing anymore. It's done, right? So then he said, okay, here, we're going to draw a tangent. And we get this. And then again, and then again, and again, and again, and again. And we will eventually get there. How do I determine x sub 2? That's the key. So look at x sub 1 and come up with an idea of what x sub 2 would be. We will do the same thing. We will write the slopes in two ways, set them equal to each other, yada, yada, the same thing. But can you come up with x sub 2? That now depends on x sub 1, not on x sub 0. Give it a shot. What is this now?
X sub 1.
Correct. What is this now?
F of x sub 1.
What is this now?
F prime of x sub.
What about x sub n plus first? Iteration. These are called iterations. So the book denotes this or says that this is the first iteration. Yes, it's okay. But I prefer to say my initial value. But if you want to call this x sub 1, that's fine. If you want to call the next one x sub 2, that's fine. If you want to call this x sub 3, that's fine. It's the same thing. I don't care. It doesn't matter. So the n plus first iteration This will be the previous one minus f of the previous one over f prime of the previous one. And this is Newton's method. And that's it. Keep in mind two restrictions. Make sure that your initial value, or if you want to call this x sub 1, that's fine by me. So the first iteration or the initial value, it's up to you, does not make f prime of x0. And then the rest will be done with the calculator. Very smooth and very easy. Okay, so let's choose a problem and solve the equation using Newton's method. So these are other interesting situations we can look at, but for now, explain how we know that the given equation must have a solution in the given interval. We can do that. And then find and approximate the solution correct to 6 decimal places. Here is a tiny step up from that previous one. Use Newton's method to find all solutions of the equation correct to 6 decimal places. I don't need all solutions. So even in when you work on Newton's method in MyLab Math, I'm sorry, we have web assigned for this class. If you find one correctly, just let me know and I'll give you the credit. You don't have to repeat and find all of them unless you want to. So let's choose any equation. For example, no one can solve this by hand. No one can solve this by hand. No one can solve this by hand. This I think it's silly because we can put it in the polynomial feature. So this one we can. But no one can do this by hand. No one can do this by hand. Solve these. But the last one is silly. It doesn't belong there. So you choose. So let's illustrate Newton's method. And solve any of the equations of your choice. And I will record the screen so I can post the videos so you have step-by-step the calculator video. But we have to choose an equation first.
20.
Okay, so we're looking at number 20. Natural log x equals 1 over x minus 3. Perfect. Okay, so this equation is the same with this equation. In step number 1, I have to create the function. I have it now. Not this. This. So natural log x minus 1 over x minus 3. Because of the equation we chose, I have to write to myself, x has to be greater than 0 and x cannot be 3. So the domain of this function is 0 to 3 union 3 to infinity. On this interval, everywhere except at 0 and 3 and negative values, I have to say that f is continuous as a difference of continuous functions. This is always continuous here. This is always continuous here. Their difference will also be continuous here. I will punch in this function in the graphing calculator and try to find, because it's continuous, by the intermediate value theorem, there exists a c in the open interval, whatever I find, as we know from a long time ago, such that f of c is 0. So if I find anywhere where the function changes sign, I will say there must be a solution there. But this has to be 1 unit interval, as we did before. Not 0 to 10, 5 to 6, 5 to 6, yes. 0 to 1, yes. -2 to -1, yes. But not 0 to 10, 5 to 15, something like that. 1 unit interval. So we are plugging it in. This part I don't have to record because it's just what we did a long time ago with plugging numbers in. So in y equals, but I will record when I start explaining how we use the graphing calculator for Newton's method. So here I have to punch in natural log, and then minus 1 over, remember parentheses please, x minus 3. So I can plug in numbers anywhere between 0 and 3, not 0, not 3, and above 3, not 3. So let's see. Of course, I know. So I'm going to plug in 1. I'm going to plug in 2. I'm going to plug in 4. I'm going to plug in 5 and 6. Okay, it's going the other way. We have to find, okay, it's increasing. Let me just see what happens at 20. Okay, so I have to go back, and I'm going to put in 0.5. Aha. And I'm going to put in 1. So my interval will be smaller because I cannot plug in 0. So you know that when I plug in 0, it will scream at me, hey, where are you from, right? So in this case, I found an even smaller interval between 0.5 and 1, which is very good for me. So I'm going to put in 0.5 and 1. Then next step, I will determine the derivative, because I need to make sure that I don't start somewhere where it's not legitimate to start with. I have to choose x sub 0. So find f prime in step number 2, f prime of x, which is 1 over x minus. So that is x minus 3 to -1. So x minus 3 to -2. So this is 1 over x plus 1 over x minus 3 squared. So can I start at 1? Yes, it's nice. This is 1. This is 1/4 because it's 2 squared. So number 3, I'm going to say my starting point is 1. Okay. So I'm going to go back and just write the function now, and then we'll punch it in. So then number 3 and 4 can be together. I like to call this function n of x, Newton of x, which will be x minus the function natural log x minus 1 over x minus 3 divided by the derivative, which is 1 over x plus 1 over x minus 3 squared. This is what I am going to plug in the graphing calculator. So this is for TI-84. This. And then I'm going to start with the first iteration to be 1. And then I'm going to copy x sub 1, x sub 2, x sub 3, as many as I need for 6 decimal digits to start repeating. And then I stop. So let me record this because I want to post it for you. Okay, so where is my recording? I think it's here. Record, yes, on this computer, yes. Okay. So in y equals, I will enter my function. Lazy people like me, I'm kidding, will enter because I already have that numerator. The numerator is there. So I have x minus parentheses Natural log x minus 1 over x minus 3. That's already in there. I used it before. So that's the numerator. And divide by the denominator. Careful how we plug in the denominator. 1 over x will work without parentheses. Plus 1 over, in parentheses, x minus 3 squared. And don't forget to close the parenthesis for the denominator. Okay? So now, after I punched in Newton's function, which is x minus the function over the derivative of the function, then I get out of there with second and quit. I go to variables, across to y variables. I am calling function y1 by pressing enter, and I want to plug in 1. That's my starting point, or first iteration, or initial value, whatever you want to name it. I press enter, and I get my first x1. I got 0.6. Now go to second and entry. It copies what you had before and overwrite the 1 with second and previous answer. So now you want the function to be calculated using 0.6. So I press enter, and I get my second iteration, 0.651165622. From this moment on, I don't have to do anything else but click, click, enter. It will automatically plug in the previous answer here. So my x sub 3 is 0.6530574313. Click, click, enter. My x sub 4, 0.653059. So I have 5 digits repeating. I need one more. Okay? So 597292. 7292. And this was the next one I shouldn't copy because it will be identical. Click, click. Everything. So I don't have to continue. So I will say, and now I can stop my recording. Where is my stop recording? Okay. So I can post this for you step by step. Okay. So then, of course. So then I'm done. 2, 4, 6. This is my approximation with 6 decimal digits. So we say the method converged, gave us the answer. Converged in, if you want to say 1, 2, 3, 4, 5, you can say 5 steps. I normally would say 1, 2, 3, 4 steps, but it's up to you. 5 steps. So the initial value was 1. We plugged in 1 everywhere. We got this. Then we plugged in 0.6 everywhere, and then we got this. Then we plugged this in everywhere, and we got this. We plugged this in everywhere, and we got this. I didn't have to write the next one because it was completely identical. If I'm asked 6 decimals, I'll say this. If you want to say, I want to round it up, you should, and change this into 60. But this is the final answer. Any questions?